Welcome to this next version of the Iliad webinar series. Today we are going to talk about standards in digital twins of the ocean. My name is Bente Lilja Bye. I'm going to be your host as usual in this series. And today we have a very impressive and numerous panel of speakers. So with that, I start to show you the program for today. But before I show you that, I will encourage you to ask questions and comment throughout the presentations, because we will go through these presentations one by one and have the discussions and questions at the end of all the presentations. But also, as we normally do, we have some polls in between. So in between each of the presentations, I will publish the results of the very simple poll that I will publish during the presentations. So we get started immediately with the program. So I will share my screen so you can see this. So this is on today's webinar. I will introduce first also a little bit about Iliad for those of you who are not partners in Iliad. We will start with an overview of standards for digital twin development by Sigmund Kluckner from IEEE. Then we will get an insight in spatial web with IEEE and the SWF. Sorry, I don't remember the acronym there. George Percivall and Nestor, an expert in standardization work from IEEE. P2874, and you will learn what that is when he presents. Working on standards with Iliad and EDITO Digital Twins of the Ocean, that will be presented by Arne Berre from SINTEF. And then we will get some insights to what is happening in the US, most particularly in the NASA Digital Twins project by Thomas Huang from JPL. We are then looking to becoming a little bit more practical, putting standards into action by Piotr Zaborowski from OGC. And then we are actually looking at a couple of examples, both addressing oil spill in Greece and see how standards play a role and can be used concretely. And then a discussion. Very busy program. So let's just start. I'm a partner in Iliad, running a company, a research and consultancy company dealing with Earth observations and their applications, and also interoperability in general. I'm the innovation manager in Iliad. Digital twins, just a quick, you will learn more about the definition of digital twins. There are multiple, but the way we see it is that the digital twins of the ocean provides a virtual environment representing the ocean, and it's capable of running complex predictive management scenarios. It's innovative systems that integrate across disciplines, sensors, models, and digital infrastructure. It's a whole ecosystem that is made interoperable. It's data intensive, of course, and we need it to be cost effective as well. Iliad in a seashell is, again, this interoperability of digital twins, so multiple twins, where we are connecting existing resources, and we are also providing new resources, including citizen science. We create a marketplace where these twins and its components are being made available to the public or those who are interested, various different groups of users of this. And of course, we are contributing to find solutions to the challenges that we are addressing and need to solve related to ocean activities. We have many individual twins addressing different topics, and it's typical different ocean human activity interactions in, for instance, in wind energy, related to harbor safety, etc. I don't want to spend time on all the different. You can see here we have 12 groups, but there are multiple twins within each of these groups in Iliad. Again, we want to make this interoperable. That's why standards are so important to us and why we have this webinar today. Iliad partnership is a part of a regional and global dynamic ecosystem. So this is also complicating things a little bit because everything is changing all the time. And therefore we work closely with other projects and initiatives, such as, for instance, one of our guests today from NASA, both public and private actors. And we try to make this aligned by using similar standards, APIs, and best practices. And it's a big project funded by the European Commission, as well as the partners. This is an innovation project. The total budget is close to 19 million euros, so it's a very substantial investment. And with that, I will go back to the program, and we start with you, Sigmund. And the way we are doing this now, I will give each of the speakers the floor, and the speaker will introduce him or herself very briefly themselves, and then we will learn about standards today. Okay, Sigmund, you are up. Let us hear a little bit about you, and we are looking forward to learn about standards, the overview that you are giving us.
All right. Thank you, Bente. Yeah, I'll try to keep it very short because we have really, really cool things going on here later on. So I'll keep it to the minimum that is necessary to set the stage for the others. Yeah, my name is Sigmund Kluckner, short Siggy. I am a digital innovation consultant working for IEEE, in this case IEEE France, and I act as the liaison as well to IEEE Standards Association. And as that, I have the opportunity right now to explain a little bit on what standards are and how we get here, and what we can do with those. Yeah, so first of all, I wanted to choke with Thomas before that. I extra chose this particular example for the US, but it's also one that the IEEE is using a lot, the Great Baltimore Fire. And the Great Baltimore Fire is one of those occurrences where standards will eventually become very important, because in February 1904, more than 2,500 buildings were destroyed or severely damaged. There were over 1,200 firefighters on scene, and a lot of these firefighters were out of state or out of the city. And the biggest problem why they couldn't contain the fire that quickly is, and you guessed it, the fire hydrants were not compatible. So fire hydrants coupling to the hoses were 600 variations in 1904 drawn over the US. So the problem was that the people were there, but they couldn't get the water out of the fire hydrants because they couldn't connect to them. Additionally, later on, the Philadelphia and New York City fire departments criticized how Baltimore was doing the firefighting, because the one part was attacking the fire from the front, and the others were attacking from the back. So they were not compatible at all, also in a process perspective. So you see how this can become important, and this is also the reason why after this, the NFPA created the standard for fire hose connections. So we're still not, the US still isn't there completely. There are still cities that have not adopted that standard, but it's getting better and better. And that is exactly why we need standards. I'm not saying that digital twins will distinguish fires anytime soon, but it is the same exact challenge that we're facing when we're looking at digital twins. So standardization, as I mentioned, a standard is a specification for, and also includes procedures that describes products, services, and processes, so that they can be universally taken up by others, that they can interact and interoperate safely, and the functionality is not severely hampered by different ways of looking and exchanging. Standards use a consensus finding process that ensures that everybody agrees to what we have discussed before, to then being able to implement it. And it includes the needs of all stakeholders, and that is important, which is also why sometimes standardization is seen as a very tenuous process, because you do need to have the majority or all on board to do this. And that rigorous process, here as an example from IEEE, the images from IEEE, I think overall they are very similar. If you ever identify the need for a standard or have an idea, you obviously have to set up a project around this. So you start to formulate a proposal, you formulate the scope and why it's necessary. You develop, once approved from the standards board in IEEE, in the IEEE's case, you develop that standard, which can take months to years until you have heard everybody, until everybody has put in their ideas and efforts and compared what is already there and so on. The standard is then reviewed. There is a comment period for some of these processes, followed by the consensus building. And consensus building can be a voting where every member who is participating in that group has one vote, or that can be consensus building where we have a general agreement or a no objection agreement that everybody basically says, yes, that's fine with us, no more exceptions. And of course, there can be consultations after the fact as well, that you seek an input and feedback from outside of the of that group as well. We have, once that's through, we publish that standard. And after that, and here, the example here is 10 years, you either revise the standard or you withdraw the standard because it has been superseded. Revision, meaning that you'd look at the current state of the art, and then you go and update this to reflect that state of the art. I already mentioned that there are several standards organizations. This is a really quick overview because there is a difference between the national, regional, and industry and theme-specific organizations. The international organizations, most known ISO, is members are national standards bodies. Regional organizations, for example, SEN in Europe, they have national standards bodies, but also include industry representatives. And then the industry or theme-specific ones are a whole bunch of people and organizations that can join in to develop standards. And IEEE SA is one of them. OGC has as well individual all the way to government entities that might not necessarily be the standards bodies. And that is the big difference. The standards for digital twins, here the reason really is, why are we even looking at this? And as with many of these standards, and not only firefighting, but everything that has to do with interoperability can be defined by a standard and can actually be supported, and even the product development can be advanced by these standards. So within the digital twins, we obviously have technical standards that are in use. We have the data collection storage, we have reference frameworks, system architectures. As Bente mentioned, the connectivity and interoperability between the pilots is important. So connecting those algorithms, models, the code potentially to be portable from one digital twin to the other, or interconnect the data that flow between the different models, of course, need some sort of a standardization, because otherwise, if somebody is putting in A and the other one is expecting a number, then there is going to be a problem eventually, right? And the same thing applies to the semantic interoperability, where we have to define standards on ontologies or taxonomies and all these kind of that we are actually making sure that we are talking about the same thing as well. And I have mentioned procedural before with the firefighters. That is also something that can be standardized. So, for example, engineering processes can be standardized. It's like, how do I do certain steps in an engineering profession? As well, the validation of digital twins can be a procedural standard in terms of looking at the actual real life equivalency, for example. There can be standards on how do I assess this, and what are the reference points, what are the margins of error, and so on. Lastly, as a list of a lot of examples and standards are out there that are definitely applicable to digital twins. Looking from the IEEE perspective, I found at least those 3 that you can see here. And IEEE has the numbering system with the P, meaning it's a running project. So the P2888 is everything around interfacing cyber and physical worlds. So this is a working group, and they have they are aiming for developing a set of standards, especially for the sensor and actuator interfaces, making sure that the orchestration works. So this is an ongoing group, and it's as far as I know, you can everybody can join as an individual. We will hear the P2874 from George later on. This is a standard on a spatial web protocol, which is done in a collaboration between IEEE and the Spatial Web Foundation. An example for a processing standard would be the IEEE 7000 that was just released in 2021, which is a model process for addressing ethical concerns during system design. So this could be one thing that we're saying, that you say, okay, I'm following the IEEE 7000 in engineering my my digital twin. We will also hear then later from Arne about the ISO work, the technical committee, and especially there on digital twins. We have also the OGZ as a member of Iliad, of the Iliad consortium, where obviously because digital twins normally of the Earth more or less always have to interface with some sort of geographic assets, will definitely come in here. And one reminder really that I wanted to make here is that the development and deployment of digital twins are based on a whole bunch of standards that you might not even think of as standards anymore. So we're using, for example, in Iliad, we're using Archimate as our modeling language, which in a sense has nothing to do with digital development, with digital twins development, but overall it helps us in making sure that all of our pilots are described in a similar fashion. So they are interoperable also in a mindful sense. Or on the other hand, like if we say we want to use RESTful APIs, they are based on the Hypertext Transfer Protocol, which has been standardized for a long, long time by the IETF. And yeah, so we already mentioned this. Iliad's pilots come from different disciplines, so they might use different standards ecosystems. So we're trying to integrate all of this. So interoperability is the highest importance for all of our work that we're doing at Iliad. This also spreads out to, for example, the development of the ocean information model as our connective tissue, which is, as I mentioned, the more of the semantic interoperability and the integration of different models and data. Arne will talk about the ISO working group, potentially a few words on this. And we are currently in discussions of putting together a recommended practice for the development of digital twins of the Earth within IEEE SA, in the sense of the procedural standard that I mentioned before, in how do I get to a digital twin development, which steps do I have to take so that these are also comparable depending on, not depending, but basically so that we can make sure that we have followed the same steps and they're up to par in the sense of the engineering as well. So if there is anything, if that is of interest to anybody, then please feel free to reach out to me and I will happily involve you in that discussion. And that's it from me. And I hand over to George, I think, well, unless Bente wants to stop to say something.
You hand over to me first, and I will actually publish the results of the poll before we give the floor to George. So I will share with you the results. You can see it now. We asked, are you using standards? And we see that most of you actually are using, some often and some sometimes. And we have some newcomers, close to 20%. So, so this is good. we can this is meaningful for the audience here. So thank you very much for participating in this poll, and there will be another one also. There will be several, but before we get to see the new poll, it will be George Percivall who will introduce us to the spatial web with the background from IEEE and the Spatial Web Foundation. George, the floor is yours.
Thank you, Bente. Appreciate that. Happy to join you all today. Good to see some familiar faces on the participation list too. So yeah, I'm George Percivall. I'm a fellow with the Spatial Web Foundation. Background is engineering of cyber physical systems for NASA, the U.S. National Science Foundation, the International Group on Earth Observation, which many of you are involved with. Also the development of open standards with ISO, OGC, and IEEE. So let me speak today a little bit about this project, this concept that's now underway. It's been underway for a while, but it's called the Spatial Web. And it was called by Deloitte a couple of years ago, the next era of computing. Let me put this in slideshow mode. That's probably better. Yes. There we go. How about that?
Thank
you. You betcha. Thank you. All right. And now the right button. There we go. So a few years ago, about 5 years ago, a couple of folks, Gabriel Renee and Dan Mapes, put together a concept called the Spatial Web, which aimed to eliminate the boundary between digital content and physical objects. So very much a cyber physical kind of approach that they laid out in this rather visionary document about where they saw that moving towards. And it got picked up in a lot of industry and consulting work and the like, Deloitte and others. And it was really about this shift from a web of pages to a web of spaces. And it resonates well with the semantic web, which and the web of things and the web of objects, those kinds of concepts. But it really kind of goes beyond that in a couple of ways with respect to the definition of space and the definition of actors and domains that relates to the AI perspective that you'll see. The technology behind that was rather broad and inspiring. Lots of moving innovations with great names, right? It's always good to have a good name that drives the marketing of the topic, as well as being, it must be based on real technology. And many of these obviously are, and in particular have come to the fore in the past couple of years. AI, for example, is all the rage right now. So what to do, right? We've got this concept of a digital twin. We've got the technologies that's behind it. We've got the concept, excuse me, of spatial web, which was written in that book and the like. So what the founders of this did was approach the IEEE Standards Association, and in particular created this project called P2874, which is, as it's stated here, the standard for spatial web protocol, architecture, and governance. So at this level of the IEEE document, it's an architecture, it's a reference model, and then it defines requirements for a protocol and an ontology and the like. It's in the IEEE Standards Association. Siggy just did a really good job with respect to what is IEEE SA all about. The particular group within SA that the spatial web is part of the Artificial Intelligence Standards Committee. And so our group about spatial web falls into the AI Standards Committee. And now, there we go. Okay, so we're underway. We've got it approved a couple of years ago as a project, developed the second draft, which was approved unanimously in January of this year. And so you see the D2 there. And well, the other thing to mention is IEEE brought this on board as a public imperative. And so they saw this a little bit different than some of the other standards and recommended practices and the like that get developed in IEEE SA, and labeled it a public imperative, given its breadth and its potential impact on the way we handle information, cyber physical information in particular. So we have a draft, and that's what I'll give you today, is a little bit of the top level outline and kind of what's in the draft to give you a sense of what's the spatial web standard, draft standard, is all about. two key concepts in the spatial web, HSML and HSTP. So HSML, hyperspace modeling language, is a modeling language, an ontology, defines a set of entities that I'll show you in a moment, that allows you to discuss domains, the spatial relationship of those, the activities and the like, essentially the top level modeling language that you need in order to accomplish a spatial web. Then you need message passing, right, between nodes in the distributed architecture. That's HSTP. And this is a bit, it does definitely have a strong query language with it, but that's tied to HSML. But the objective here is to make HSTP pretty thin and put it on top of things like HTTP, MQTT, and other existing protocols. The beef, if you will, is in HSML. So here's the ontology, the HSML entities. There's 5 entities and the relationships between those that allow you to do computable context in cyber-physical systems. And so we'll speak quite a bit in the next couple of slides about domains and spaces, but also take note of the couple here that I won't speak too much about, and that is activities, channels, and credentials. And so having in this interactive ecosystem of agents and information, the ability to define activities, get contracts on those activities based upon credentials and identity, and then have a channel in which activities play out is a key aspect of the spatial web and how things are accomplished. But let's describe perhaps what's a little closer to digital twins, and that's domain and space. So HSML domains, a top level entity in the HSML ontology. A domain is any sphere of knowledge, influence, or activity. So it's a very abstract concept. It certainly immediately makes you think of geospatial domains, which correlate, of course, to geopolitical, geophysical spatial regions. But the domains can go beyond that, and in particular, knowledge, influence, and activity. It's a set of abstractions that allow you to discuss knowledge in the sense of here's a concept and here's its relationship to other concepts. So it's a domain modeling language, if you will. And in particular, it's anticipated to build a universal domain graph, which is the domain of all domains, in a graph structure with a very particular structure to it that allows you to do queries on it, allows you to interrogate it semantically to determine questions of interest, say, about an ocean domain, and then what is its relationships in terms of, chemistry, physics, and the like of the ocean domain to other domains or internal to that domain as well. All would be part of not only the universal domain graph, the UDG, but also within an ocean domain graph. The other key element entity that I'll speak of in HSML is space. And so this is our summary diagram of the types of spaces which are addressed by the spatial web. And so it's a generalization of what you might think of space, especially if you've got a geographic background, like most of us who live on the surface of the earth have such a background. So vector spaces, right? Whether it's earth-centered, earth-fixed, or it's on the surface with northing, easting, and up. Those kinds of vector spaces that we're familiar with from, say, GIS, or remote sensing, or any kind of coordinate reference space in which you're addressing things that are tied to the surface of the earth. But that's not the only space in which we can discuss concepts, in particular abstract data types, really driven by machine learning, in which now we're talking about n-dimensional spaces where n may be tens of thousands of dimensions, allow us to discern the differences between apples and carrots based upon this abstract data space. And so that was a real driver behind the concept. And then, of course, the graph type spaces, whether it's a flat graph of nodes and links, or it's a hypergraph that brings those together, or the bridge, if you will, between graphs and coordinate spaces being cellular spaces, in particular, making use of DGGSs and H3. And so this is the spaces that we deal with in the concepts of spatial web. Related to those topics of identity and credentials and activities and permissions and contracts is a whole set of governance activities, which I list here in brief. Let it be known that there's a lot of detail to this, but I sense it's probably not the immediate concern of this more physical modeling activity of the oceans domain. So, but it's really critical to achieve the contextual interaction of agents in an open domain with contracts and the like in order to accomplish activities in a fashion. The protocol, I mentioned, it has a conceptual model. There's conceived of 2 bindings right now. It's been bound to MQTT on occasion. HTTP in particular, web APIs are the other, and it's mostly message passing. There's not real, it's CRUD type activities. And there's a set of distributed computing use cases that describe how to make use of HSTP to accomplish the activities in a set of scenarios, application scenarios. So the use cases are the building blocks, if you will, of distributed communication that leads you to value, which is in the applications. So let me tell you about the applications that are sketched out in the document. They range over over geographic and social scales. So across the top, social scales from enterprise to humanity. Across the left there, geographic from indoor to global. And some of them are pretty straightforward. These are well implemented over on the left, and the things that are being developed right now are the things that are of most interest to this group. We have 2 that have the digital twin flavor to them. One is an urban digital twin, in particular with smart cities, and it has to focus, the one that's in the document is focused on electrical energy and the ability to work with the grid being, in this case, the electrical grid and the management of that grid using the domains and the spatial web protocols. The other then is the digital Earth model, which now is, Earth digital twins and the like. In particular, of course, focused on greenhouse gases, negotiation of reduction of greenhouse gases using AI agents in this negotiation ecosystem of greenhouse gas, and carbon trading is the way to think of that comes out in that scenario. So, the objective here is to apply this technology to things like climate and energy, as I've just discussed. And I really look forward to increasing the discussion with digital twins. Because I think these provide us not only the static and dynamic aspects of physical models of our world that are so key to these activities of the spatial web and how they get accomplished. So I leave that there and look forward to the discussion.
Thank you very much, George. You have got questions for your presentations and also Siggy. And as I said, we are collecting them. So we are giving the people the opportunity to ask at the end. I assume you can stay the whole 1.5 hour, George? Yes. So let us then share the results, because George asked you an interesting question. Which of the technologies combinations will be most impactful in the next decade? And here you see the results, George. Artificial intelligence and IoT got 55% of the votes. Artificial intelligence and digital twin, and it's nothing to do with ice. I got 33%. It's a spelling mistake, sorry for that. And then AI and the metaverse got 12%. So thank you again for participating. We are taking care of this interesting gauging that we are doing. Thank you very much. And thank you, George. I will then,
thank you.
Yeah, I will give the floor to Arne Jørgen Berre. You will talk about working on standards both in Iliad and the EDITO digital twins of the ocean.
Thank you, Bente. So as you see on the slide here, it's also about enabling semantic interoperable digital twins through data spaces, data lakes, and relevant APIs and ontologies, using also IoT and AI technologies. The wider context of the work in the European context is related to Destination Earth, which is a large program that includes a number of digital twins currently ongoing, weather-induced and geophysical extreme weather twin, and also climate change twin, managed by ESA, the European Center for Medium Weather Forecast, and EU METSAT. But there are new digital twins that are on the agenda. So we are in the ocean digital twin, also related to biodiversity twins, and there are more that are coming. So this is a large effort. The digital twins of the ocean has also an international aspect to it. Here is the DITO Digital Twins of the Ocean program from the Ocean Decade under the United Nations auspices. And we see the idea of a digital twin here, that there is a connection between the real world to the left, digital twin world to the right, with observation, sensor data models that are being visualized and understood, giving insights, leading to decisions, leading to interventions, and then continuous observations and monitoring in the circle. So the what-if scenarios will be part of the insights and the decisions that will lead to various interventions. DITO also has a set of definitions of digital twins, which are relevant, of course, when we talk about what they are. This is specialized for digital twin of the ocean. We'll give some pointers to more general digital twin definitions later. But basically, virtual representation of the real ocean with a two-way connection with it, with this feedback cycle we saw. Observations from the real ocean change and refine the twin. Manipulating the twin can highlight regions of the real ocean in need of better or different observations. A set of working groups and activities are related to this in DITO. Here is a set of working groups which also relates to areas of digital twins. And I'm involved in working group 5 on architecture, design, and implementation, or so-called Turtle Group, led by Brenner from SINTEF Ocean, also related to resources we have in the Iliad project. This is only one project that is adding input into the European digital twin of the ocean. As we see from this picture, there is a number of activities leading into observations and data, such as the Blue Cloud project, Aqua Infra project. We have the satellite Copernicus data, we have eModNet. There is a number of activities, so there is a large family essentially that are all contributing into digital twin of the ocean under this umbrella. The European digital twin of the ocean here is highlighted through the project that is led by Mercator and LIS. It's actually a subdivided project, the so-called EDITO Infra and EDITO Model Lab. We see the concept of a data lake, bringing data from a lot of different sources, including Iliad, eModNet, and others, into the data lake, and then a digital twin engine that will support analytics and simulations and various kind of models with AI and predictions for a lot of different domains, which we see around kind of the globe here, with additional information for biochemistry, biodiversity, socioecology, and other things that will enhance and provide a set of digital twins that can interoperate. The Iliad architecture, which coming up here, shows the planet up on the top, and the various domains of pilots and demonstrators that provide data and observations from many different sources on the left here, including new sensors and observations, a lot of different other sources that been brought in, and overall data space that links all of these things in an accessible and a harmonized way, so we can use this data in a common reference framework together with, say, both historical and real-time data, as a focus for local and sector-specific digital twins that also associate analytics, AI and prediction simulations, and tools that provide the support for decision recommendations and visualization, and further to actions and control. So it's an underlying digital twin pipeline. We see on the bottom here that all of these twins are following: data acquisition, digital twin representation, digital twin models of the data, but also hybrid and cognitive models, including AI and machine learning, combining with physical models, and the visualization and control. If you look into this, we see a lot of areas of interactions with APIs and service interactions, and the actual standards that we are working on, looking into how we can benefit from, both in the EDITO and the Iliad, are related here on the ISO SE41 on IoT and digital twins. That's the ISO home for digital twins, and the working group 6 on digital twins that already have ongoing standardization activities, such as ISO 30173 on digital twin concepts and terminology, the 3186 digital twin maturity model, new work item on digital twin reference architectures and digital twin use cases. Also a recent proposal here on IoT for ecological environmental monitoring, which is relevant, and also link back to the initial definition of digital twins under Industry 4.0 from the Industrial Digital Twin Association, and also the ISO 23247. And then AI has been mentioned multiple times, so ISO SE42 on AI and big data, and the European Sense and Elect JTC 21 AI provides AI concepts and terminology, AI frameworks for machine learning, also related to data for AI through the ISO 2546 and 47 on big data architecture. And also there we have use cases, including digital twins. And also interesting an area that are emerging now on AI and data quality. A new work item on data spaces, linked to data lakes also here. From Europe, we are concerned about the AI Act, how that can be also brought into the standardization activities. We have seen concepts and words like data spaces, hyperspaces, data lakes, and this is also ongoing in an industrial context. From the European point of view, the European Common Data Spaces is a large set of projects led by the Data Space Support Center, DSSC.eu, with Gaia-X and IDSA. So there is 10 plus different projects that are evolving there. Also data spaces for Green Deal, particularly the GREAT and the All Data for Green Deal projects. Iliad is a Green Deal project in terms of funding. And of course, we have a foundation in what we can call geospatial digital twins with standards from OGC and ISO TC211 on geospatial API standards, which are focusing on entities of interest in time and space, slightly different from the Asset Administration Shell perspective, AAS, which is more traversing machinery or windmills with the different parts. So we see also these two digital twin approaches as complementary and supportive of each other. Further, we have data models and ontologies, work that is ongoing with the content of services and interfaces that can be described in different ways, say ontologies and RDF and OWL. Also, how we illustrate architectures and models with UML and Archimate, which has been mentioned, which are also standards, by the way. And the work on the ocean information model and the link to evolution of standards. So both George and I have previously been involved in the ISO 19119 on geospatial services with ODC also. It might be time for an update on that in this context. And we have other initiatives such as the European Open Science Cloud that have a data service marketplace. We have eModNet, ERDAP as an interface to time, space, or spatial temporal data is perhaps not a standard, but also relevant to open source community. And we have work in the UK on a digital twin information framework, which has some link to British standards that are looking at interoperable federated digital twins. And also industry standards on digital twin. We have the Digital Twin Association that has contributed to a digital twin vocabulary, and also an interesting digital twin periodic table of different areas of concern along a digital twin pipeline. And this is not all. There are other things, so I didn't mention the IEEE here, but there is a lot of ongoing activities that Iliad and EDITO will relate to and contribute to, and also use results from. And perhaps we'll discuss a little bit further kind of what are the most important standards to follow, or maybe areas where results are evolving and areas where results are needed. So that was my overview, I think.
Yeah, thank you very much, Arne. Again, I'm just going to say that these slides will be made available for you because there's a lot of information to absorb here. But the slides will also be made available along with the recording. Now, we had a poll during your presentation as well. I will share that very quickly before we go to over the Atlantic to NASA to the US. So here you see Arne Jørgen, he asked, what is the most important to standardize? Concept and terminology got 18% vote. Reference architectures, just 4. APIs, and this is the big winner, APIs, services, interfaces, and protocols, 52%. Models and ontologies, 26%, and that was it. So thank you again for participating. This is very interesting for us all to contemplate on and to gather this information, because there's a huge group of experts on the standardization here. I can see from the list of participants. Arne Jørgen, thank you very much. And now we are going to you, Thomas. Are you ready?
Okay,
to
can you
share?
hear me?
Yeah, we hear you.
Oh, good. I had a network problem earlier. Let me move my screen a little bit. Can you see my slide?
Yes.
Okay, very good. So thank you so much for the opportunity to share our work today. I'm Thomas. I'm from NASA JPL. Today, I'm be talking about the open source framework for digital twin that my team has been developing for a couple of years now, really. And my primary job is a group supervisor at the NASA JPL, and also the principal investigator for the digital twin efforts at the NASA Earth Science Technology Office. Click on this. So I think we have a couple of definitions of digital twins already, and I'm just going to summarize it in just one liner, right? It's all about the what if, right? Being able to develop a technology where you can allow the decision maker or researcher to ask the what if scenario. And this is actually a complex question because about our Earth system is quite complex. And rather than just think about technology per se, is really about connecting the valuable science and solution together and help us make a better decision or finding interesting information about the world that we live in. Now that's the short answer. Now, if you want the long answer, you can go to this website. This is actually the Earth Science Technology Office at NASA. They actually released a high-level description for Earth System Digital Twin. Very similar to some definitions from our previous speakers. The expectation of the digital twin is really to identify building an integrated solution for multi-domain, multi-scale digital replica of the state and temporal evolution of the Earth system. Really, this require us to bring in developments, model simulations, continued and timely observations. This is including satellites in situ, IoT measurements, and also collecting long-time records, right? And also be able to provide things like analytics and artificial intelligence. And so if you want to find out more, there's a whole portfolio of different digital twin efforts that's funded by the ESTO office in NASA that you can go to and find out more through that website here at the bottom. Here's a summary on the technology that we're building under my projects. So if you look at the center diagram here, the blue area is the physical world and the yellow area is the digital representation. And the outer ring is really the components of this, right? The key here, I think this is similar to my previous speaker here, is that you have the aggregated data service. This is where the data harmonizations, bringing all the data and model outputs into a simple analysis optimized platform. Drive that solution to help us run the numerical simulation and also for AI predictions. The prediction kind of will help us make the decisions. And so the requirement for prediction here is not just creating a plots or what it might look like. We really want to be able to develop actionable predictions, things that we can do, right? Decision maker might be thinking about how to mitigate or relocate the asset. Or better yet, right, NASA is also looking at is how do we acquire the next observation? Like, can we retask the satellite? Can we go acquire, deploy UAVs to take observations? Or if they're ground station that we can actually connect to acquire more data. And that information brings into another, basically a holding where we can actually onboard the data into the digital twin. So the system is continue to improve over time. So I think the group here know this, right? Digital twin is this big data problem, and big data is, the more we talk about it, it gets bigger every day, right? So my model is really about being smarter about what data to use, and so means that don't try to build a bigger system, but build a system with the relevant data, being dynamic, being able to bring in what's necessary at that time. So relevance is extremely important, but more importantly, it's sustainable. I come from an operation background, so I want to make sure when we build technology that it's actually sustainable over time. Means that can we put somebody and extend it throughout the years? And what's the cost of operation? Do I need to put a team of people to run this, right? And what's the total? Do we just put this onto the cloud, or can we? How do we make the connection between different systems seamlessly, right? So we recently published a book about some of the building blocks that you might be interested in looking at. So it's about information community, right? Let's face it, we can build we never gonna be able to build a big enough digital twins, right? It's all about being able to create a community or interoperable services. So we've been quite successful over the years, right? We developed some open source solution for analytic engines. And throughout the years, we deploy all of these across the globe, and they share the common APIs. And the user, which is in the middle, where they can just use Jupyter Notebook or GIS applications, they can just connect to these services through simple APIs. So this group here is talking about ocean. I came from ocean background. I spent 15 years in the NASA Physical Oceanography Data Center. So on the right side, you've probably seen some of this plot, right? These are two plots actually generated through distributed analysis. We have a Jupyter Notebook that actually talk to two different systems. One is computing, pulling the echo sea surface height. The other one is actually connecting to the NASA sea level change portals backend for the measures product. And you can actually, the user won't have to replicate any data. They just need to make the call and they generate these plots. And it's likewise the same thing with comparing echo with the Grace follow-on products. So the group here is talking about a lot of standards. Well, obviously we look at a lot of standards in the building this framework. And definitely, I mentioned before to the organizer, we definitely looking at the process APIs. We also look at the sensor things APIs as a way for building digital twins. Interoperable connecting with the European partner. We actually looking at WPS and WMS, WMTS. Exposing the system to the user, we actually look at standardized stack, open search, ISOT, and also there's something that's still missing, analytic APIs. There are no APIs really, as far as I know, that actually being used widely by the community about like, hey, can you just give me a time series? Can you give me a non-linear plot on this? There's nothing like that yet, as far as I know. Maybe this group can point me to some options. So I see this as a framework where you can build application on top of this. And you can connect it with the Jupyter Notebook. Again, you can draw your VR, you can build your scenario-based questions, which we had one up here talk about. What happens if we reduce 35% of the emission in California, like get rid of the engine's car in 2035, and how many deaths can you prevent using the digital twin? We can actually get that answer. We're also using this to connect with our European partner at CNES with their flood efforts, which I will talk about later. But in the back end, we are using these API to connect with services. And particularly the process API is what we use to connect to a numerical model. One of the models actually runs on a NASA HPC. Actually, it's not in AWS or Amazon Cloud. So how do you bridge the cloud to the HPC? And then we also have some models that should run on the cloud. Can we use a common API and make it seamlessly to the user of the framework, not having to care about where this model is actually being run? So, so first application using this framework is the work that we are collaborating between NASA and CNES-led effort, actually funded by these Space for Climate Observatory on their flood dam effort. So it's really creating a federated digital twins. As you can see, we have a large group of people supporting this project. And really some of the high level question, right, that we look at is what are the environmental infrastructural impacts of floods, right? And again, we have two digital twins here. We have the NASA ones that we just talked about, that I'm talking about as a framework. And then in the European side, they are building also focusing on models and also infrastructural impact. And so we're building bridges between the two systems. And here's a summary of this, right? The NASA side, we actually running simulations on pulling the latest precipitation or rainfall to estimate the surface and subsurface runoff. This is in the French region. And we can actually use that runoff to drive our another model called the rapid, which is once discharged. So now we know where the water is going. And then we can compare that with the IoT that's collected on the bridges right next to the river that we can actually see at the actuals. But with that discharge, we can actually use it to estimate the river height, the water height level. And this is where we're at right now. Like this is all connected with multiple model and observation and all work seamlessly together. And the next step is using this river elevation, we can estimate what is the infrastructural damage and cost. And that's another effort that we'll be working on. Now, ML is a big one here. Remember, we have lots of in situ observations. We have lots of data, and I just talked about being smarter about what data to bring in. So we're building ML model to help us to identify areas of interest instead of trying to bring in all the data in and say maybe we'll use it later. Well, this is where the area we think is actually going to be impacted the most. Let's pull those data sensor observation into the system. And that's what we're building in the back end. So the end is all about communication, right? So I talk about a bunch of APIs in the early slides. We released a notebook to the public. This is actually a URL to the notebook that you all can run. And you demonstrate all the current API and data that we're managing for the flood digital twins. And it also can generate animation on the fly for you and run all the interactive analytics. And the reason I released this notebook is also to help bridge communication between us and our French partner. And so they know how to work with our system. And of course, when you're building digital twin, now you have an API, you have a platform. Why not build a VR experience, right? This is the VR environment that you're looking at with the same data that you saw in the Jupyter notebook, but now in a fully immersive environment. The second application is about wildfire and air quality that we're working at. And this is a different group of people. We're working with the city of Los Angeles, the National Institute of Environmental Health Science, and of course, with one of the upcoming missions that NASA is launching called Maya. And it's about, one of the questions like, what are the environmental health impact for in wildfires? Relate to wildfire, right? As you know, I live in California. Wildfire is actually very relevant to me. And this is actually a very personal project to me as well. Again, very similar, using the same framework. We bring in all the measurements and models, and we release a notebook where we actually can interactively analyzing things like PM 2.5, ozone. We can actually we actually have an interactive application that runs on your phone. And all in funny is about in situ. So one thing that we did, we actually installed some of the in situ IoT device on top of one of the buildings at JPL. And if you know where JPL is, we're actually right next to Rose Bowl, which is a huge football stadium. And every July 4th, we have fireworks. And we actually kicked up the signal and see the emissions about PM and black carbons as a result of the fireworks in July 4th. Right on top of the building at JPL, and we were able to bring this data in live into our system. Again, it's all about digital twins. We have VR for connecting or accessing the same data. And finally, one of the examples that we try to build out is using the same ML capability. We are collaborating with the Maya mission, which you can find out more about this website from the website above. That we can actually try to retask the camera on the instrument to take additional observation if we detected some of the areas of interest. So that's something that we'll be discuss more if you come to AGU this year in December. I'm definitely going to have more update for you. Again, we're about the community. We actively working with the open source community. I've been doing open source for more than a quarter century now, so I'm really old. And we are making all the data and software available. We're hosting webinars. We share recipes. The goal is really try to make the software solution reusable and available to the public free of charge, right? This is all, again, it's not owned by NASA or JPL, it's actually owned by Apache Software Foundation. So in conclusion, the Earth system is a very complex and too expensive to accurately be represented by a single digital twin, right? We all building digital twin, right? And I call it islands, and it might sound like negative things, but we all building digital twin. We need this. But let's also build bridges, right? Can we connect these islands together, right? And bring all the best information together, and let's make them interoperable, right? At the end, Earth system is really the system of the subsystems, right? And to me, as my definition is that making software, using reusable framework, making open source, and using standard is the bridges, right? Again, I also want this group to know is there's no golden standards, right? I've been doing this for over 2 decades. Standard changes. Your goal is standard is, to me, is more about generalizations. You also have specialization, which is how you implement your system. Your system has to be able to adapt to different standard over time, evolved, right? That's part of the sustainability. So with that, I'm going to stop here. If you have any further questions, feel free to email me. This is my email, and happy to have further discussion.
Thank you very much, Thomas, and I'm worried for your schedule. I will wait to publish. I will simply ask quick questions in the chat because they are asking. There are a couple of asking if there are notebooks available for the public to use. Both Jupyter notebooks for NASA and also GitHubs. Are they available?
Yes, they are on public GitHub. That's the whole point. We build everything in the public open repository. I'll share the slide with you, and it has a link to my notebook.
Yeah, right. So then send us your slide deck, Thomas.
Okay.
If you don't mind, because I think that it was super interesting and we have so many things in common. So we should maintain this relationship we have started to create here. Yes. Thank you very much.
Thank you for having me, and I do apologize for having to leave early, and but really excited to work with this group here, and thank you so much for having me.
Excellent. Drive safely.
Yeah. Bye.
Thanks. And I see we are behind the schedule, so I will politely ask the next speakers to be efficient. We are a little bit behind. I would really like us to have some time to discuss as well. We have collected some questions. So without further ado, go ahead, Piotr. Now we are going to be more hands-on.
Yeah, exactly. So I'm happy to follow up this discussion within the Iliad and around, because there's a number of things that well, the consortium needs to implement if they want to do this digital twins within the project. We have a number of things to be implemented, and we are trying to use the standards as much as possible. Sometimes we have some needs as well. So this will be more about the practical approach. If you don't know the standards itself so much, or maybe you don't want to implement them on your own, you are not connecting, you are more providing these data or services to this digital twin. And naturally, you are all aware that these well-known standards as Bluetooth are quite flexible, and that's the reality. So we have the flexibility within the standards, but we also have the functionality that helps to recognize what are the capabilities of these stakeholders. And that's probably somehow related to the agents and web approach of this geospatial information, to be able to connect the different devices in different manner. So I'm not surprised this reference architecture is problematic, because it's always about being in really flexible way. So if we want to provide the interoperability of this of our services, naturally there's a number of questions, not limited to those, but there's a couple of things in terms of geospatial information you want to share or you want to consume. What is your data? Who are you actually in this process? Do you integrate with the process and the value chain, or are you integrated vertically? Are you passive or are you interactive with this infrastructure? And also the manner of the access plays a role. So I will briefly focus on these three cases. We've met the need that the participants in OGC and in this projects, for example, wants to explore expose their data sets to be findable, filterable, and understandable, or even fair. So data sets are usually kind of repositories that has the footprint, so they have the areas of the interest, but they also have some more details, and there's a need to drill it down. Then the other case is that you have the netcdf file. Simply, you are the modeler and you are providing simulations. You produce these files. You want to expose them in efficient manner. You can also have this first scenario when you have the measurements directly. You have the data streams of these measurements, and you want to make it available and understandable. What's the sensor? What is the characteristic of measurements? What are the conditions maybe? And how do they relate to each other? So going through different cases from Iliad, this is not the whole picture of the APIs that are being in use within the community. I will just now focus on these three cases, meaning features, coverages, or EDR, environmental data retrieval, and the sensor things. We have also the others, like the OpenDAP, VerDAP, which are not OGC. We have also some in progress, which were invented and initiated within the project itself, like synchronization API. And most of them are supporting, they are modern, so they are supporting this model approach. They support the security patterns, will not go deep into security. Therefore, fine-grained access control is supported, while not actually needed so much in this project, at least from what I know. So go to the first scenario. Going to the first scenario, we want to make our data visible, and here naturally what nobody likes is the metadata description. Nobody likes to describe their data sets and then put it in this let's say standardized way. But there's a number of things you may need to provide, and within the Iliad we are working on these templates. We are working on these templates that could be used to set up this scenario. Here in the presentation, you have the links to the repository. You have the sample configuration. You will get some familiar things like the footprint of these data sets. You will have the description, but you will also have a number of non-standard properties that we can add and will add in this project. Then you have the second configuration that goes to the data set level. Here you are providing the provider information. So who are you? Who is the owner of this data set? What's the license that you applied for that? You can have some additional definitions in this higher level. So based on actually these two files, you will go to this repository. You will find a very simple instruction how to set it up, just using these two files, but you can also put some other data inside, and you will get this kind of service. You will find this HTML, JSON support, but just a digression now. I mentioned that the standards are flexible, so it's worth to know that also the OGC and other geospatial standards have some functions. So there is a way how to describe this functionality within OGC APIs, and there is a way how to discover what are the possibilities within these functions. And knowing that, we are now providing this multiple protocol API for this for our dataset register with the information what is it about. So can it play the music, or can it be controlled by my watch, or can it be controlled by my car? You can also have some additional fields like the functionalities description, like what can I filter the data with. So I have the open search, I can use the open search, and I can use it with this kind of fields. And this is just with these two files, with this reference implementation, this is what you can set up. And naturally, we are trying to connect these different registers. So we know that there are outside of Iliad and inside of Iliad multiple domains, and the ontologies and graphs were mentioned several times. Within the Iliad, we want to also link it together with these different perspectives. So we are aware that there are different scenarios that have different, that are domain specific, but we also have this cross-domain views. So on this level, on this pilot specific level, this is a cross-domain ontology that inherits with this generic one. Going to the second scenario, I will come back to this OAM in a second. Going to this second scenario, when just to remind, we have the numerical data coverages in the netCDF. For those who don't know, this is the netCDF metadata. So you open the file, you read it, and you get this kind of information, meaning that you have some data and metadata inherited in this source file, like domain, properties, and ranges. Some other you need to provide in addition. So once again, there's a link in the presentation I will not open now, but there's a sample configuration. Just take this configuration, put your netCDF file and see if that works for you. And with this one configuration file and one reference implementation, and in Python, you can set up this kind of services. This is providing already support with different encodings on the clients. You can filter the data, you can slice it with some basic functionalities like getting the data from the point, getting data for the bounding box. Some more sophisticated are partly supported. So in the standard, you have the trajectory filtering and slicing. You have the corridor as well. Not all of the implementation naturally support all of the functions. And this is just the example. You've seen that in the netCDF file, the properties are mapped directly to this interface. But this is just a pure EDR. I mentioned the ocean information model, which is giving the explanation of what are the data, meaning that we have the temperature. In the ocean information model, we have this typology, so we know what type of information is that. And going further, we even have these reference to the observer property. Either it's defined on the on Iliad level or outside. And in the first scenario, which is implemented by PNCC now, we have the sensor observations. So the scenario goes from the CSV file and the citizen science information that's, let's say, structured in this Excel or spreadsheet way, meaning that it's somewhere. We want to expose it in a coherent way with this ocean information model. And with this example, also you have the links here. You can get out of this CSV file this kind of interactive interface to use. What's the advantage now? We have the harmonized way. We have the information with ocean information model, meaning that we have direct links with the definitions of what we are actually describing. we have it on the web, not somewhere on somebody's computer. And we have this functionality of messaging, querying, and browsing, meaning that this file is not so big because this is only 6 megs, but in the database, naturally, you can store a lot more, and you can filter what's actually needed for your scenario. You see here some different, some strange signs. This is actually comments in Fabric, and this ocean information model supports also this multilinguality of the definitions. So what we are doing now and next is to support these pilots with these harmonization, meaning that there are a number of databases in the files. We are setting up this demonstrators to provide this coherent view of this ocean information model through the APIs, meaning that within the repository we'll collect these cases and provide the sample configurations for the cases. We will support the implementation of the connectors. Naturally, not all can be done on my side. This will be collaborative work. But what's important, we are providing this on the layered architecture process. So we know that we will not change the legacy systems, at least all of them. We know that some of these modern APIs are also provided within the consortium and outside. So first step is this technical harmonization. Second step is only this uplift, and the uplift can be done within the implementation and as the additional layer. So I was fast or not?
Well, you were fast, but we are so delayed, and I'm just calculating that we have about 4 minutes for discussions afterwards. If we are staying within the time frame. We were afraid of this happening, but so we have some questions, and some of the questions has been answered in the chat as well. But I feel like before we are using this a few minutes before we actually show another very good example, 2 examples from Georgios and Katerina. I would like to ask George Percivall, since we have you here now, that you can answer the question we have a couple of questions for you. So we take that before, and then we will see how many can stay. I can stay on, but I cannot assume that everybody can stay on beyond the 1.5 hours we have warned about. Let me see for George. Yeah, it was Alexandra who asked, why create another language, HSML, while you already have the OWL?
Yeah, so the web ontology language, spelled out OWL, OWL from W3C, is very good, as well as RDF that underlies it, right, in defining the structures of an ontology. It does not have the entities that are in HSML, for example, like space, domains, activities, and the like. So it's anticipated, in fact, it's already been done a couple of times. The HSML entities have been implemented in different profiles. And so there's a JSON profile of HSML. And then, I'm anticipating there's going to be an OWL profile. And there's also a BFO basic, formal ontology that actually gets into some space activities, space and time activities that are kind of interesting. I anticipate that might be also another implementation of HSML. Hopefully that helps, Alexandra.
Great.
Not entirely, because it's about creating new ontologies rather than creating a new language. So your case seems like in need of new ontologies, because OWL is a generic ontology creation language, development language, rather than, and also GeoSparkle is around, so for the spatial element. So there is already something. Why do we need to create something on top of what already exists?
Because they don't describe the things that we're describing, is the short answer.
Yeah, so sorry about that, but you could be creating a new ontology that would actually accommodate your needs, because it seems that you need ontologies rather than to cover your needs rather than a new language.
Oh, absolutely. We're creating an ontology. There are many ontologies already existing, more to be created. And there are tools to create ontology. And I would suggest OWL is a tool to do ontology engineering. It does not express all of the entities. If you go look at the OWL spec, right? The entities of interest to HSML are not in the OWL spec. So one way to create the HSML implementation is to use OWL, absolutely. But you have to define what those entities are, space, domains, an example. They're HSML defined entities so that you can put them into the OWL tool set, as well as other tool sets.
Yep, thank you very much.
Yeah.
I see that we can deepen and have more webinars in topics here. So sorry for interrupting this interesting discussion, but I think, so thank you, George. I think now we definitely need to give the floor to the last two speakers, Georgios and Katerina, who has been very patient. Georgios, you can start your presentation, and while you are getting ready, I'm just sharing 2 comments. Identifying standards and that standards too complicated are bottlenecks for use of standards. Thank you, George.
Okay, thank you. Thank you, Bente. I'm Georgios Sylaios from TIMECODES University of Thrace. I will speak about the best practices in operational oil spill modeling. For some reason, okay. So this is a diagram which shows that since 1970s until today, there is a gradual and continuous decrease in oil spill incidents over the decades, which is, of course, a result of technological advancements. The fact that we now, in shipping, they use the double hull ships rather than the single hull, and overall the legislation will become stricter. So there are plenty of tools we have in our disposal to monitor and forecast oil spills. There are the satellites, the well-known satellites, the SAR systems. There are the drones now, several sensors moving in the sea like the gliders, or the static sensors like buoys. And then we have what we are trying to really explore in Iliad, which are the low-cost sensors, and we try really to use them and integrate them in the existing systems and collect data of physicochemical parameters of the water. And all these data are assimilated in a series of models. In oil spill modeling, we have to consider a series of processes which are taking place when we have the accidental release of oil in the sea. So there are physical processes like the evaporation or the advection, the spreading of oil, but then we have a series of chemical and biological processes like the dissolution, the sedimentation, the emulsification. One of the most important is biodegradation. Biodegradation has been overlooked through the various numerical models and is not really well described. Biodegradation is the response of the marine environment through a series of microorganisms to try to decay and degrade the oil and in fact reduce its toxicity. This is the data frame, the frame of models, and how we see the series of models that we have to use in oil spill modeling. As you can see, oil spill models cannot be run by themselves. We have to combine them and couple them with existing other models, like starting with the atmospheric models, in order to really understand the velocity, the direction, the speed of the winds, and other meteorological parameters. We need also to consider the hydrodynamics of the area, especially the currents, but also the stratification dynamics. Then we have also to consider the wave dynamics, the wave changes in terms of the significant wave height of the wave spectrum, especially the Stokes drift. And finally, the biogeochemical models in terms mostly on the concentration of nutrients, the content in the dissolved oxygen and the bacterium concentration. All these affect the dispersion and the weathering of oil. And we have, of course, to consider the oil type from existing oil libraries, and utilizing all this data in combination with the remote sensing in order to detect the presence of oil spills, and a series of algorithms which are automatically detect the oil spills. We assume that at the end we will have accurate results in operational forecasting. This is a table from a recent review we submitted in a journal where we are reviewing the various atmospheric models and the providers of the models, the geographical coverage, and the spatial resolution. And we find that there are plenty of products which are already available. We don't need to reinvent the wheel. We can go to these global products and downscale them, or even utilize regional products which are already available and freely available to use. Most of them are used for the forecasting events. Some of them are used for hint casting. There are, in terms of hydrodynamic modeling, again, a series of hydrodynamic models, and here we review the providers, the geographical coverage, and you see here, for example, the Copernicus data products, but of course there are plenty of regional products that someone can use, and the most important, of course, is to pay attention to the spatial and temporal resolution which these products are providing in order to force in an appropriate manner the oil spill model which was selected. And then in terms of wave forcing, again, we see here that there are plenty of wave systems providing wave data products. The providers and the geographical area with the global products and the regional ones and the spatial and resolution. Here, I just want to say that one of the things that we find really interesting is the impact of the waves and how the different investigators are considering the waves in their oil spill simulations. Here you see, for example, that we have 3 different cases where we run the same model and we force it with wind data from ECMWF, the hydrodynamic data, and also the wave model. They are coming from Copernicus, from Swan, or from wind-induced waves directly from open oil. So we have 3 different outputs, 3 different results, and this shows that we have to be very careful when we are considering the forcing functions in the operational oil spill models. Now, when we look at the 24 cases, 24 publications, recent publications in oil spill modeling, we will see that very few of them are using waves in their configuration. And when they do, they use waves with considerably high or coarse spatial resolution and very, very coarse 12 hours wave fields provided by the different wave data providers. So I think that this is something that has been overlooked, and we in Iliad are trying really to refine it and to consider it. And this is a slide which shows what we are doing in Iliad in terms of the oil spill in the digital twin framework, where we are developing the algorithms to scan the satellite images for oil spill. We are also scanning the media, the social media posts for any oil spill references, especially the Twitter. We use citizen science apps to record the oil spills from citizens. And based on this is the event identification pack. We are triggering a series of models. As you can see, the hydrodynamics, the waves, the biogeochemical models. We also use machine learning models and algorithms in order to improve the downscaling process of the wind speed and direction, and to forecast in a better way enforce in a better way the oil spill model. And then we alarm the authorities, based on which, again, using the social media, we are able to evaluate whether the cleanup operations and the mitigation efforts have been successful. So as a conclusion, I would say that high resolution wave models should be coupled to oil spill models in order to have better results. Biogeochemical processes have been overlooked, especially biodegradation, and I think Katerina Spanoudaki, who will speak after me, she will pay some attention to the biodegradation rates. it's important that we need to further improve the parameterization of these soil weathering processes, especially biodegradation, and emphasis should be given on the assessment of the accuracy of the oil spill model results, especially when we have the results to compare them and find some indicators, and this is also some part of the research we are doing, the appropriate indicators in order to compare the model outputs with the satellite imagery. Thank you.
Thank you very much, George. Very nice to see an example of the use of various standards. And now we will dive deeper into the ocean, actually, with Katerina. And I quickly give you the floor because of the time. So we will see another oil spill example with a slightly different perspective. Katerina.
Okay, Bente, don't worry, I will be brief. to collapse. Okay. Okay. So I'm Katerina Spanoudaki from the Foundation of Research and Technology in Greece, and I will directly pick up from where Georgios has left off, actually, and give you a little more insight into the best practices in operational oil spill modeling. I will use some experience and example from the Great Sea Iliad Digital Twin. Just to give you a short background for the motivation, this is the area that we're focusing in for the Iliad Digital Twin. It's an area of very high economic interest, and the most important part regarding our pilot, our oil spill pilot, is that we do have exploration exploitation activities for offshore oil and gas, which creates huge concerns the local authorities.
Katerina, we are not seeing a presentation mode. So we don't see you moving your slides, and it's more we see your speaker mode, I think.
Okay, I don't know how to fix that.
And the slide wasn't moving either, so that's why we need yet another version. Yeah.
Can you see it now?
We see it, but we see your still the speakers. You as a speaker, we see two slides, one big and one small.
Okay.
She has two screens, and she should use the other screen for showing us.
Yeah.
No, I've changed just one screen. Maybe I will try to.
You don't remember what you did to begin with, right?
No, I really did the same thing. I will just stop my video. Maybe this.
Alexandra in the chat says, click on the
Ρυθμίσεις εμφάνισης. Yeah, Katerina, you can click on where it says ρυθμίσεις εμφάνισης, and then there are two choices. If you bring it up, you can choose one of the two, and then we can see the presentation mode.
Okay. Now?
Yes.
Yeah.
Yes. Okay. Yeah. I'm really sorry about the delay. I'm really confused now. You're saying full screen. So pick up where I left off. So what the authorities expect from us is when an oil spill happens, they need to know what happened. So where the oil spill was, where it will move to, how soon it will get there, and what the state will be when it arrives, and most importantly, what are the resources that are threatened. So Georgios already showed this I think something like that. This is how it translates what the authorities expect from us in operational oil spill modeling. And Georgios has mentioned what is important for atmospheric, ocean and wave models. And I will talk a little bit more about the oil spill detection, the oil weathering, and why it is important to have nutrients and dissolved oxygen information. Just a little bit to tell you about the best practices and standards in operational spill modeling. There are many recommendations from REMPEC, for example, for NOAA. There is one international standard, and we have also done some work giving some recommendation best practices in operational spill modeling assessments. So what the standard describes is that we need to include at least the basic weathering algorithms, take into account local conditions, so where you apply your oil spill model, ingest and integrate external observations like satellite data, and be able to adjust the predictions to update the observations. Otherwise, the forecasts do not make any sense after a couple of days, and estimate the uncertainty for both the fate and the transport of the oil spill. So this is a general idea of our oil spill DT, and it is very similar to what Georgios has shared for the Russian CDT. So while you have different tools, so different metocean models and oil spill models, we do have some synergies, especially in Earth observation ingestion. And we also use Iliad as a means to be able to interconnect our digital twins and have portable and relocatable algorithms, codes, and models, and be able to exchange our and reuse our data, which I think is really important in the frame also of this webinar. Coming to the satellite data integration for the oil spill cases, we are working together as a group with DUTH and the MEO, and for of course, hope that others can join as well. At the moment, we're testing SAR data from Sentinel-1, and we're using the OEM index in order to be able to detect oil spills from satellite data. The idea is to have a list of events, to be able to test the algorithm in oil spill detection, then train the algorithm, test the replicability, see if we can have replicability globally. This will help us with faster response during emergencies, and the idea is to, of course, remove the human interaction. We're in digital twin world, so we need to have automatic operational chain. And this is our end goal, and integrate this into our forecasting systems in Iliad. And regarding now the uncertainty estimation, which is also important, it is recommended as a best practice. We are integrating several different sources of metocean data in our digital twin, so high resolution, coarser resolution from for both oceanographic forecasting systems and meteorological data in order to be able to assess the sensitivity for both what the metocean forecasts and forcing impose in the fate of the oil and the transport of the oil, but also what the uncertainty of the data coming from and being integrated from satellites or from a user regarding the starting point of a spill or the date that the spill has occurred, and be able to show this as a probability factor, so the most probable location or fate of the oil, and not just one deterministic approach. And I will close very briefly what we are doing with some challenging and improvements that are needed in oil spill models. So we are dealing very much with the microbiological degradation. It is one of the most important processes. It is what attenuates the impact of oil spills, and it is really what saved the worst outcomes from this large Deepwater Horizon accident in the Gulf of Mexico. So it was the ability of the nature to degrade the oil. The truth is that it is overlooked in operational models. They do not consider it, or if they do consider it, they consider it a very simple first-order kinetic process. They do not take into account the effect of nutrients or dissolved oxygen. So we have looked at that a little bit more in our models. It is a work in progress, both in a deep sea oil spill module and in the surface. We are considering the effect of both nutrients and dissolved oxygen, and we're using monokinetics. So we do take into account the bacterial concentration, which feed into the oil droplets. So we're using a shrinking core model. The microbes feed into the oil droplets. And it is very important to have local data in order to be able to have very impactful assessments, especially in the case of weathering algorithms and biodegradation. And this is why you cannot really measure bacteria. You can take samples from deep sea water or surface water and see how indigenous populations feed on the crude oil. So we are in collaboration with HCMR and Technical University of Crete and collecting samples from deep sea water in order to be able to see what is the degradation efficiency of local indigenous bacteria populations for the southeastern Mediterranean Sea, and how the southeast Mediterranean can react to a possible large event of a deep sea oil spill. I think I will close with that, and thank you very much. If you want more information, you can contact me or my colleague Sabrina from MEO, who is really working hard with DUTH for the oil spill identification from Earth observation.
Thank you so much, Katerina, and thank you all for staying on so long. Thank you to all the speakers also being very patient.